Hello, I'm here to introducing our project accelerating MCTS rollouts with CUDA AlphaZero. So our main goal in this work is to leverage parallelism to speed up the Monte Carlo tree search, which is MCTS, particularly the rollout phase. So to make AlphaZero train and play much faster. So for the background, AlphaZero is a general reinforcement learning algorithm that learns to play complex board games like chess, Go, and Othello, entirely through self-play. So at the heart of the AlphaZero would be the MCTS. So the MCTS works by building a partial game tree, like using four steps, which are selection, expansion, simulation, and backpropagation. And in particular, the simulation phase, also called the rollout, um, is where MCTS plays out a random game from a newly expanded node until a terminal state is reached. So the result is then backpropagated up to the tree to inform future moves. So there would be a converted into a numerical reward. So there would be like a reward value like representing the result. Um, so here's the important part. Each rollout is independent. So this makes the simulation phase embarrassingly parallel and therefore a perfect candidate for GPU acceleration. So um, for the rollout acceleration, so we decided to do the rollout acceleration, and in traditional CPU based implementations, um, rollouts are done sequentially, like one after another. So the runtime would be very big. Um, so when we need like thousands of rollouts per search, this quickly becomes a major bottleneck. So our project idea is simple, um, but powerful. So we move the rollout phase onto the GPU and assign each independent rollouts to its own CUDA thread. To demonstrate the feasibility and performance benefits, like we chose a simple game like tic tac toe. So tic tac toe is the 3 by 3 like zero sum game. Players like alternate like placing X or O on empty squares and first to occupy an entire row row column or diagonal like wings. Um, so um, this game like preserves the essence of the tree search like without like overwhelming complexity. So like for design details, a sequential CPU based MCTS would be our baseline. Like it should be look like this, and um, how it works. So like for each iteration, like we perform multiple rollouts. Like each rollout is executed like one by one. So you can see like it's purely sequential. So the runtime like grows linearly with the number of rollouts. We'll see in the performance later. So like for the GPU acceleration strategy, so that we created a CUDA kernel. So for the kernel design, that would be the key part of our project. Um, so each CUDA thread handles one independent rollout, and um, the initial board state and current player like are copied into each thread's local memory. So there is another like important thing is there is a state representation that it is structured, and so it's a flattened array. So we use the array, which is the states of length n rollouts multiplied by 10, like holds the game state for each rollout. So originally it would be a very complex structure on the AlphaZero, but we uh, use the flattened array here to more like clearly represent the game state. Um, oh, and one more thing to mention, for integrating and profiling the full AlphaZero pipeline, would be like too complicated. like first semester on GPU. So we isolated it and we decoupled MCTS from the neural network and implemented pure MCTS search on this game on the tic tac toe. So it like just preserves the core tree search logic while like allowing us to focusing on the acceleration, the rollout process. Mm, so like the execution flow would be load. So we copy the initial board and player in like into thread local strut state, and then ensuring that, like a subsequent access hit registers. And the second thing would be randomness. So it loads a variable called like a current state, like into a variable, like uses a current to like do the sample moves. And the third thing is simulation, and the last one would be write back. So we write the D results like back to the RNG state. So we write back the results into the state here. So there would be our kernel design. So it will look like this. Um, for the memory layout, it would be three things, but the most important two structures are D states and D results. So the D states is an array of size n rollouts multiplied by 10, like for ball states and current player. And the D results, like representing our simulation results, which is an array to store the winner of each rollout. So, and then for the host device transfers, will be like very simple. So there will be four states, I suppose, all three states. So it will be upload. So the before our kernel launch, host packs the current node state into like a host vector H states, and we use the CUDA mem copy to copy it to the D states, and then we execute the kernel by running the kernel call, and then we download the like after the kernel run we copy it back to the copy our reward results back. Um, so. And for the performance part, so you can see for the CPU performance, so CPU scaling, the CPU runtime like grows linearly with the number of rollouts. Like you can see right here. So this reflects like the purely sequential nature of the CPU rollouts loop. So for example, like you select thousands of 1,000 of rollouts, and the 5,000 rollouts. So the 5,000 rollout would be like five times of uh, the execution time when the rollout was 1,000, and so on. So and for the GPU like constancy, so the GPU like timing remains like nearly flat, like across like increasing rollouts for the like same thread configuration, because like the GPU parallel threads like amortize the per rollout work. So like launching thousands of rollouts in parallel hides much of the per iteration overhead. So even like doubling the workload only slightly increase the total kernel execution time. So you can see that would be the 7, 8, 9, 10, something like that. And for like when we change the thread numbers, it would be a insensitivity right here. So what is insensitivity? So we change the thread per block, like it only like yields almost identical GPU runtimes. So it indicates that all tested block sizes achieve like sufficient occupancy to fully utilize the GPU's compute units. So the the total number of threads here would be the same, but the structure of the block and the threads like layout would be different. So, but the total threads would be the same, so will not have a big difference here. But once the GPU is saturated, like redistributing the threads among blocks does not like improve throughput or like reduce latency, like very much. And for the future directions, So we would like to like extend the GPU parallelism like beyond the rollout phase, like for the parallel selection phase, and also for the batch propagation phase. So we can like accelerate the parallel selection phase um, by the like reorganizing the tree data structure into arrays. So we can launch a GPU kernel that evaluates the UTC score. So there will be a score for all children of a node in parallel. So we can accelerate by um, like reorganizing the structure. And for the batch backpropagation, so the results of the tree like can also be batched. The a parallel kernel could like update visit counts and values for odd ancestors of multiple leaf nodes simultaneously. So like a used and like efficient like prefix sum or like segmented scan approach. So for future directions, these kind of these two phases could be also parallel, like parallelized. And for the contribution part, so Rory implemented the baseline CPU version of the MCTS, including the sequential rollout and game state management. And he also implemented the random number generation with current for parallel rollouts and developed the data structures and memory layouts for GPU rollouts. And for Hongwei, he integrated the CUDA kernel into the MCDS pipeline and handled like host device memory transfers. And Hongwei also designed and wrote the GPU kernel, a rollout which is rollout kernel to parallelize the rollout phase. And also he like conducted the performance testing, collected runtime data, and generated the plots. And thank you so much for your attention. Here would be the code implementation demo. So the most important three like data structures are D states, D results, and RNG states. So for the D states, it holds the board and current player. The D results holds the simulation outcome, and the RNG states holds random number generator states. So here's our main CUDA kernel. Each thread represents a separate rollout and loading its own initial game states and performing a random simulation until the game ends. Um, so we allocate device memory on GPU for states, results, and random number generator right here. And then we like transfer the initial board states from the host to the device, and we launch the GPU kernel, like rollout kernel here, like where each thread simulates a full game independently. And at last, so we copy the rollout results back to the host for aggregation. So we can then analyze the simulation results. So let's make some run here. So for let's do based on the report. Based on the performance here, so we selected like 128 threads right here, and we make different rollouts, and we can run the code to see the execution time for so make thousands of rollouts here. So the GPU execution time would be 12 milliseconds. The CPU would be like 2,535 milliseconds. And if we increase the number of rollouts to 5,000, so the like the CPU execution time will like increase linearly, like the 5 times of the previous 1,000 rollouts. So if we make it like to 20,000, so increase linearly as well, and the GPU execution time increase as well, like as long as the rollout number of rollouts increases. And then for the different like number of threads, like I described before, like it will be in sensitivity. Um, so for like when we change the number of threads per block, so it yields like almost identical like GPU round times. So let's make a round here. So we select thousands of rollouts. We try 64 threads. So you can see the GPU execution time would be 10 milliseconds, and CPU would be 2000 something. And we increase the thread number to 128, so it does not like change a lot of the CPU execution time. But and also for this CPU time measurement. So if we increase it to 256, it also like does not make a big difference because the insensitivity, so the because of the layout of the block and the threads, so it indicates that all tested block size achieve like sufficient occupancy. So that would be the demo for the code implementation.